Let's discuss free fall. When air resistance doesn't affect the motion of a falling object, when the only force acting on the object is that due to gravity, we say the object is in free fall. Here we have a boulder, heavy enough that air resistance is negligible for short falls. Phil Physiker drops the boulder over the edge of a tall cliff. Since only gravity is significant, the boulder experiences free fall. We'll only discuss free fall here. The falling boulder picks up speed as it falls. This pickup is acceleration. Acceleration equals the time rate of change of velocity, given by the equation A is delta V per delta t. For straight line motion, we can use the terms velocity or speed interchangeably. Recall that speed is the magnitude of velocity. In free fall, during each second of fall, the exact same pickup of speed occurs. We say the boulder falls with constant acceleration. Here's Phil at the top of a cliff, ready to drop the boulder over the edge. He drops it, and it accelerates downward. Wouldn't it be nice if a speedometer were attached to Phil's boulder so that we could watch the gain in speed as the boulder falls? We wouldn't be able to see the readings, so we blow up the speedometer for better viewing. We start from rest, so the speedometer reading begins at 0. This is our initial speed. Our speedometer also has an odometer that measures distance traveled. Its reading is set to 0 at the time equals 0 mark. Phil releases the boulder with its speedometer, and 1 second later, the boulder is gained 10 meters per second during this 1 second interval. The odometer reading is 5 meters. That's 5 meters, not 10 meters, as we'll explain later. For now, just concentrate on changes in speed. 1 second later, the boulder again gains 10 meters per second, and the speedometer reading is 20 meters per second. And our odometer reading is 20 meters. 1 second later, the boulder again gains 10 meters per second, and the speedometer reading is 30 meters per second. And our odometer reading is 45 meters. And another second later, another gain of 10 meters per second finds the speedometer reading 40 meters per second. At the 4-second mark, we find our boulder has fallen 80 meters at the instant its speed is, as said, 40 meters per second. Let's make sense of these readings. First, the acceleration. We see that acceleration equals delta V per delta t equals 10 meters per second per 1 second equals 10 meters per 1 second multiplied by second, which equals 10 meters per second square. Notice how the symbol for second appears twice. First, the time and velocity, and second, the time during which velocity changes. That's why the second squared. How do we know that the acceleration of free fall is 10 meters per second square? Because we've measured it time and time again. You can do the same with actual measurements in the lab, where you'll get 9.8 meters per second square. To simplify calculations, we round this off to 10 meters per second square. We call the acceleration of free fall g. That's g for gravity. From g equals delta v per delta t, we can say that delta v equals g delta t. Or, simply, equals gt, which reads, the speed gained in an interval of time t is equal to the acceleration times that time t. Since g equals 10 meters per second square, we can write speed gained as v equals 10 meters per second square times t. Notice how this equation accounts for the white speed readings. At 1 second, v equals 10 meters per second squared times 1 second equals 10 meters per second. At 2 seconds, v equals 10 meters per second squared times 2 seconds equals 20 meters per second. At 3 seconds, v equals 10 meters per second squared times 3 seconds equals 30 meters per second. At 4 seconds, v equals 10 meters per second squared times 4 seconds equals 40 meters per second. How about distance fallen? Here's where equations guide our thinking. From the equation for average speed, we know that distance traveled equals average speed multiplied by time. That is, d equals average speed times time, where average speed is v sub 0, our initial speed, plus v sub f, the final speed, divided by 2, multiplied by t. And we see our initial speed in this case is 0, and v sub f is the final speed at time t. And we have distance equals 1/2 gt times t, and t times t is t squared. So the distance fallen is 1/2 gt squared. Instead of d, we substitute y, the common symbol for vertical distances. For numerical values, distance of fall is given by 1/2 of 10 meters per second squared, which is 5 meters per second squared, multiplied by t squared. This agrees with the 5 meters, 20 meters, 45 meters, and 80 meter odometer distances of fall. Got it? Not really, until you've given some study time to this. In this lesson, we've considered the simplest case of free fall, starting from a rest position. Suppose instead that Phil Physiker throws the boulder downward, rather than dropping it. Suppose he imparts an initial speed, v sub 0. The speed when a stopwatch begins at 0. Our equations can take this into account. Instead of v equals gt, we say v equals v sub 0 plus gt. That is, the speed at any point will be the initial speed plus that gained by acceleration. And instead of distance y equals 1/2 gt squared, we add y equals initial speed times time. So the falling distance will be that due to an initial speed plus the distance it would fall due to acceleration. Getting back to falling from rest, initial velocity 0, I leave you with 3 questions. Question 1. At 5 seconds, what will be the speed of the boulder? 2. How far from the top will it have fallen in 5 seconds? And 3. What will be its acceleration at this 5th second? Think about that. Until next time, good energy.